Okay, page 2, question 2. A radioactive isotope is decaying at a rate of 18% every hour. Currently, there are 100 grams of this substance. Write an equation that will represent the number of grams present after an hour. So I'm going to use the variable g for grams, right? So I'll just say I've got g grams of this substance. And I'm starting out with 100. And what's happening is every single time an hour goes by, 18% of it goes away. Now, the way that we think about this is a decay, right? So it's decreasing. If 18% goes away, that's interesting. But what I'm interested in more is what part stays. And it's actually 82% that remains. So every single time an hour clicks by, I'm multiplying by 82% again, 0.82. And where we get that from is we start with 100, right? And we subtract 18% expressed as a decimal, and we get that that's 0.82. So 82% remains when 18% goes away. So that's in our equation that models that. That's Finn. The next it says, how much will be left 1 day from now? Well, a day is 24 hours, right? So we're considering when n equals 24. And the amount that will be left behind then will be 100 times 0.82 raised to the 24th power. So let me grab my calculator and evaluate that. So we're starting with 100. And I'm going to multiply that by a bunch of 0.82s, right? Every single hour gets a new 0.82. Of course, we don't have to multiply that out by hand. We just say, oh, we want to multiply by 24 of those, right? So it's 100 times 24 factors of 0.82 times 0.82 times 0.82 times 0.82. When we do that, we get, it's actually less than a gram, right? We've got 0.854. So we have less than a gram. We've got 0.85 grams approximately. So how much will be left one day from now, 24 hours from now? 0.85 grams. The next thing is when will there only be 1 gram left? Well, I'm pretty sure it's less than 24 hours from now, because 24 hours from now there's not a gram. So what we're considering is this. I want to know when there's 1 gram left. So I'm going to write 1 gram equals 100 times 0.82 raised to the nth power. So for this equation, what I'm concerned with is the value of n, right, that makes that right-hand side equal to 1. Now, it turns out this is an exponential equation. My variable's up in the exponent. And I told you earlier this year that the only time you had to solve these was when you could rewrite the equation so that the bases were the same. That's impossible with this. But most recently, we've considered, hey, let's look at this as a system of equations, and we're trying to figure out when the left-hand side equals the right-hand side. So if I take that approach, I can model this fairly well on my calculator. I'm going to say the first equation I'm going to graph is just going to be y is equal to 1. And on a standard view, this is what it looks like, right? That's the line y equals 1. And I want to find out when that line meets the line 100 times 0.82 raised to the x power. Oops, not times x, raised to the x power. Now, one of the things I know about that is that its 0th term is 100, and then it goes to 82, and then it would go to 82% of 82. So each time it's going to multiply by 0.82. So I think if I graph this, my standard window shows no intersection at all. I know from this first problem, this part up here, at 24 hours, it will cross it at 24 hours. So what I'm going to do is I'm going to change my window so that x is going to run from hour 0 to hour 24. And I'm actually going to make it, let's run it out 30 hours, because at the very end there it's going to cross. I don't need to see negative 10. I'll make this go from 0, maybe from 0 to 10. Let's see what this looks like. I might play with this again later. So there's y equals 1, and there it is. Yeah, that's a great view. That was a very convenient window. I'm very happy with how that looks. Now, when you see these things, the important thing is that I can see the intersection, and if I can see it on this screen, then I can find where they intersect. You may not be as lucky as I was that time. You may have to rescale the window some more. So don't be afraid to think about, your domain. X starts at a value, X goes to a value, and what's your range. And just play with the domain and range in the window until you find something that you're happy with. At this point, I want to find out what exactly is the value of X in this case, right? It's n in the equation, but the value of X that makes these two curves meet. And I can easily do that by just looking at the calc function. So I'm going to hit second calc. It's on the same button as trace. And when I do that, I go to option number 5, which is intersect. So in order to find the intersection of two curves, I need to know what the curves are. So the calculator is asking me, hey, what's the first curve? And you can see it's flashing right now on y equals 1. So I'm like, that's good. So I'll press enter. And then it says, what's the second curve? And it has up here 100 times 0.82 to the x. Now, it turns out I only have two curves graphed currently, so that seems like kind of a silly question, but potentially I could have 4 or 5 curves on the screen at the same time. But given just these two curves, I'm just going to press enter again. And then it says, well, what's a guess for their intersection? So I'm just moving my cursor down, and it's, somewhere in this neighborhood. You don't have to get really close. I got it around 21 hours. Then I press enter, and it's going to find, and there it is. You see it found at 23.21, right? So I'll write that down at about 23.21 hours. So it's an hour and then 21 hundredths of an hour. I could convert that into minutes, but I'm just going to leave it as fractions of an hour or parts of an hour. Now, what's nice is on my screen right now, you can see X is currently a value. If I leave the graph and I press X on the screen and press enter, you can see it's got that very value there. So which is really convenient because now I can just check, is it really doing what I think it's doing? So let me show you this. I'm just going to go up and grab that equation where I type the 24. I'm going to come up and I'm going to delete the 24. So I'll delete the 4, delete the 2. And then I'm just going to go up and grab that 23 and place it there. So now you can see I'm evaluating this expression, 100 times 0.82, to this particular power of x. And when I do that, I should get something very close to 1. And I would say that that's very close to 1. So at around 23 hours, right, and some number of minutes, it's going to be about 1 gram of it left. All right, so that's it for question number 2. Let's move on to question 3. And it's kind of related in a way. They're trying to drive home this point of how we can use graphs to solve linear equations. So let's look at this equation. It says, consider the equation 4x minus 3y equals negative 2x minus 9. Solve it. So I'm going to solve this equation. Pretty standard fare here. All right, 4x is equal to, and I'm adding 3 to both sides as a first step. And I'm writing that down just because, let's see, negative 9 plus 3 is negative 6. Just because if I have it there, if it doesn't work, I can try and track down where my error was. I'm going to add 2x to both sides, so I get that 6 times x is negative 6. And if I divide by both sides by 6, I get that x is, I believe, negative 1. Now, the next question is, how do you know your solution is correct? Well, I don't yet. However, I'm going to go ahead and take this value, x equals negative 1, and I'm going to place it in the equation in both places, negative 1, and see what it gives me. So over on the left-hand side, this becomes negative 4 minus 3, which is quite nicely negative 7. So when I put negative 1, it becomes a negative 7 on the left-hand side. And over on the right-hand side, when I put in a negative 1, I have this negative 2 times negative 1. Negative 2 times negative 1 is positive 2, and positive 2 minus 9 is also negative 7. So how do I know this solution is correct? Well, I would say because this value of x makes both the left and right-hand side equal to. Let me write that down. Obviously, this was a poorly designed test. The person who wrote it didn't leave enough room for us to write our answers down. Whoops, that was me, sorry. So it says, I just wrote x equals -1 is the solution because it makes both sides of the equation equal to -7. And that's the heart of an equation, right? What's the solution? It's a value of x that makes this equality statement true. And you can see when I plug in -1, it doesn't make both sides -7. So let's move on. Part B says graph the following system of equations, although that wasn't written. So on the first equation of this system, I've got a y-intercept at -3, and I have a slope of 4, so I can go from here up 1, 2, 3, 4 over 1. It's kind of off the graph a bit. So let me instead go down 4, 1, 2, 3, 4, and back 1. I can go down 1, 2, 3, 4, and back 1 again. So you can see these points are all collinear. Let me grab the ruler and line them up. So when I line these up, really focusing on the lower 2 points because that upper point is questionable to me. I think that's close. I'll just draw that line that goes through there. So there's the graph of the first one. You can see my y-intercept is at 3, and I've got a slope there of roughly 4. The next equation, I have a y-intercept at -9, and I have a slope pattern of -2, so I'm going down 2 over 1. And I can go up 2 and back 1, and you can see there they're meeting. Up 2, back 1, up 2, and back 1. That's great. So if I draw that line, which is, it's a little redundant because I can clearly see where they're meeting at this point anyways, I can see that, hey, these two equations have an intersection point, right? And it happens precisely at the moment. Oh, look at this, I can make this a vertical line. It happens precisely at the moment when x is -1, right? When x is -1, they're meeting. And when they meet, right, when they meet, it happens, just so happens that y is going to be the number -7. So there's the graph of the system, and I can see the point where they intersect. Now, part C says, how do parts A and B relate? Well, at this point it seems kind of obvious, but let's go ahead and take a stab at it, right? So in the first case, we're just solving a system of equations, right? We're solving just an equation. In the second case, it's like we're taking the left-hand side and the right-hand side and making them their own functions, right? The left-hand side becomes y equals 4x minus 3, and the right-hand side becomes the function y equals -2x minus 9. And what's nice is now we can track multiple values of x and y for those individual systems or individual equations and figure out where they line up with each other. And where they line up is precisely the value of x that we found in the equation case, part A. So let me write down a response here. So I wrote down the value of x equals -1 causes both the left and right hand sides of the equation to be equal. It causes them to be 7. For the -7. For the systems of equations, both lines, right, y equals 4x minus 3 and y equals -2x minus 9, both lines cross at this value of x, -1, when their y values are -7. So what we can see, and this is really related to the previous problem, right? In the previous problem, I needed to know where this left-hand side, right, y equals 1, matched the right-hand side, 100 times 0.82 to the x. And the point where that happened ended up being the solution to that particular equation. I didn't find it by solving this equation. I found it by finding the location of where those 2 points met on the graph. And that basically, that value of x was the solution to the equation. But I found it by finding where these two curves intersected. And I think that's the point of question 3. It's just kind of reinforce this idea that if I'm not sure how to solve an equation because it's particularly difficult, or it's one that I just don't have the skills yet, logarithmic versus exponential forms, I can always attempt to find solutions by just graphing both the left and right hand side and seeing where those curves meet. All right, let's move on to question 4. This is the last question on this page. It says, given the function f of x equals 2x minus 3, describe the transformation described in each part below, and write a new equation for the transform function. So you can see in part A, I've got f of x, and I'm going to be decreasing all of the output values for 2. Remember what f of x represents. It represents the output when I put in a particular x. So when a particular x goes into this function, f of x is the notation that represents that output. So what I'm saying with this is I'm saying every single output is decreased by the number 2. Now I can rewrite a new equation, right? Instead of writing 2x minus 3, I can look at 2x minus 3 and then subtract an additional 2. So g of x, this new function, could be 2x minus 5. And for a description of that, it's basically g of x is f of x shifted down 5 units. And so let's do the same thing with, and actually this is the same thing. So we're not modifying what's going in as an argument. We're just modifying the output again. So you can see here, f of x is the output of that function up above, and we're increasing all of those output values by 0.5. So what we're essentially doing is we're just kicking this entire function up a half of a unit. So g of x then would be 2x. There was a negative 3 plus 0.5, which would mean it's negative 2.5. So again, now this g of x, right, so now g of x is f of x shifted up 1/2 of a unit. Alright, so that's it for page number 2.